What control problems must the brain solve to learn a new motor behavior? Obviously, that depends on the properties of the musculoskeletal plant that's being controlled. But it depends also on the capabilities of the spinal cord, a complex and highly evolved structure that coordinates the activity of muscles. In fact, most vertebrates can perform efficient and adaptive locomotion using the spinal cord alone, with no brain at all. We're developing models of what happens at each of the levels of the system, brain, spinal cord, and musculoskeletal system, so that we understand how they work together to allow us to learn and then perform complex motor behaviors.
MSMS, or musculoskeletal modeling software, provides a complete set of interactive graphical tools that allows its users, whether they are engineers, researchers, or even non-programmers, to develop realistic models of biological limbs and prosthetic limbs and simulate their dynamic interactions with the objects in the environment. Let's start with some scanned bones linked by joints into a skeleton. A new component such as a muscle with its tendon can be added to the model. Its anatomical properties and tendon path can be modified by repositioning attachments to the bones and adding wrapping objects that constrain its movements at the joints. Here is a simplified model of a planar arm with hinge joints at elbow and shoulder, and pairs of monoarticular and biarticular muscles, which we will use in the sample control problem that follows. MSMS converts the anatomical model into a computational block that represents its mechanical dynamics and physiological properties. Each of the 6 muscles can be activated via activation input signals. An embedded model called virtual muscle computes the force output of each muscle, which depends complexly on its activation history and its current length and velocity. Visual muscle also estimates the energy consumption for each muscle, which depends strongly on its velocity and mix of muscle fiber types. Another embedded model called virtual sensors represents the populations of proprioceptors in each muscle, including Golgi tendon organs, which sense muscle tension, and muscle spindles, which sense a function of length and velocity that depends on each fusimotor control by the central nervous system. The forward dynamic model then computes the trajectory of joint angles, representing the motion of the limb, which can be used to animate the anatomical model and visualize it in 3D from any perspective in real time.
Now that we have a model of the musculoskeletal plant, we must decide how its sensors and actuators are connected together in the spinal cord, which coordinates much of the motor behavior. Fortunately, models of the spinal cord circuitry have been meticulously developed over a century of neurophysiological research. Most muscle pairs can act as synergists or antagonists depending on the dynamics of limb motion. They require additional interneurons that can be effectively switched in or out by the brain depending on the task. This is a programmable version of the multi-input, multi-output regulator that is used in complex engineered systems. In order to perform a task, the brain must send commands to set the many gains of these interneurons and their various input signals. For this planar arm model with 6 muscles, there are 400 such gains to be set. Let's see how well the brain can apply a very simple learning algorithm based on gradient descent to adjust the very large number of gains in this high-dimensional system. We will start with the simple task of maintaining posture in the face of a large, brief impulse applied obliquely to the hand. The passive musculoskeletal system is knocked far off position by this perturbation. If we set all of the gains of the spinal regulator to random values, the behavior of the system will change, but it will still be very unstable. Our biosearch algorithm simulates trial and error learning by making simultaneous changes to all of the gains according to a distribution function that depends on progress toward good enough performance. After about 40 iterations, it is much improved, but still rather spastic compared to a human. After a couple of hundred iterations, performance has settled into a plateau that is about as good as a typical human faced with such a task. If we start the learning process again with a new set of random gains, the biosearch algorithm again quickly and invariably finds a good enough solution. But note that the plateaus for each solution are slightly different. In fact, the solutions themselves are noticeably different, both in terms of the visible motion and the internal gains. The spinal-like regulator seems to have evolved to make it easy for the organism to solve new tasks quickly and reliably. the high-dimensional control space that is created by the spinal-like regulator seems to be full of local minima that are good enough for tasks and easily discovered by trial and error learning. This has obvious survival value for a biological organism, but it has some important implications for engineers and clinicians. There is no way to invert this system and compute globally optimal solution. Each of the good enough solutions may be similar functionally, but they probably differ if used as starting points to learn modified tasks. Sensory motor control turns out to be easy to do, but hard to understand. We may struggle to understand a lecture about locomotion, but we had no difficulty actually walking to the auditorium. It's important, however, for us to have quantitative models of the process, because that's how we understand when it goes wrong through disease and injury, and how we design treatments that can help with those clinical problems. When airplanes were first invented, there were no models of aerodynamics, so ideas had to be tested by building and crashing a lot of physical airplanes. It would be impractical and dangerous to build modern jetliners that way, so engineers have developed and rely on computer models of proposed new designs and their aerodynamics before they build and test the real thing. The actual test results, in turn, help to refine the models themselves, creating a virtuous circle of design and engineering. Advances in brain-machine interfaces and mechatronics make it possible to develop technology to replace function in patients with amputated limbs, spinal cord injuries, and strokes and traumatic brain injury. All these models of the musculoskeletal system and parts of the nervous system that we and our many colleagues are developing and validating are designed to let us understand what goes wrong in the sensory motor system when people have injuries or diseases. And having those models will let us efficiently design prosthetic systems and treatments and train patients in their use so that we can overcome those disabilities.